This is AP Calculus 3.2. Today we're going to start learning about implicit differentiation. Implicit differentiation has a lot of uses, especially when we get into the related rate problems. Those are some real-life problems that are important to know this method so that they can be solved. Otherwise, we wouldn't be able to solve them. If you look at this equation that I've got here, your directions are going to say find dy over dx. Now, we've learned that dy over dx is a symbol or a notation for find the derivative. So that's the same thing basically as y prime. And when I'm solving these problems, anytime I take the derivative of a y term, I have to include the symbol for dy over dx or y prime so that I know that at the end of the problem what I have to do is get all those y primes together and then get that y prime or the dy over dx by itself. Now, most of the time when you see these types of problems, teachers just use the dy over dx. Anytime they take the derivative of the y, I tend to use the y prime and then replace the y prime with dy over dx at the end of the problem, just because it saves me time and I don't have to write this every time I take the derivative of a y term. The purpose of learning implicit differentiation is, if you notice in this equation that we've got here, normally when we find the derivative with respect to x, the derivative of y with respect to x, the y is on one side completely alone. It's already isolated. But if you look at this equation, there is no way to get y isolated and have any kind of an equation that is going to be we're going to be able to differentiate. We're going to use implicit differentiation anytime we have this situation where y can't be taken over to one side and isolated. If they tell you to find dy over dx and it's easy to get y alone, I would always go with that method unless they have specifically said to use implicit differentiation. If they don't specify and you can get y by itself, that's probably easier. But in some instances like this one, there's no way to get y completely alone. So we have to have a way to find the derivative of y when that happens. And when you do that, you're going to find the derivative of each term separately, just like you do when you have a polynomial with all x's, like a y equals 3x cubed plus 4x squared minus 2. Okay? You're going to take the derivative of each term separately, but the difference is, anytime you have a term that has a y in it, you're going to tag the dy over dx beside that term so that we know that there was a y there. For instance, right here, if I take the derivative of negative 4y, the y will drop out. It'll just be negative 4, but I need to include the dy over dx so that I know that was a term that was a y, that had a y value with it. Okay, so I'm just going to go through and do this with you and explain what I'm doing as I go. When you take the derivative of y, remember you have to include the dy over dx. When you take the derivative of x, you do not have to do that and because we're taking this derivative of y with respect to x. That's why we need the dy over dx every time we take the derivative of y, but not when we take the derivative of x. So let's just take the derivative of this using implicit differentiation. Remember, anytime I have a term that involves a y, I have to include dy over dx as part of my answer. So this term, the derivative of negative 4y is negative 4. I took the derivative of y, so I need to include a dy over dx. This term is a constant. The rule still holds true. If you take the derivative of a constant, it is 0. So this term will drop out. This term, minus y to the 4th, when I take the derivative of that, that will be minus 4y cubed. I took the derivative of y, so that I need to include a dy over dx. For this term, I've got minus 3x squared. That was x, not y, so I do not need a dy over dx there because it's an x term. And in this one, I have negative 3y squared. That had a y, so I need to include dy over dx. The next thing I need to do is I need to isolate the dy over dx because our directions say find dy over dx. So that means we're going to get dy over dx alone by itself. So I'm going to move everything that has a dy over dx to this side, anything that doesn't to the right hand side. So when I do that, this stays where it is. The minus 4y cubed stays where it is. The negative 3x squared goes to the other side as a positive 3x squared, and the negative 3y squared dy dx goes to the other side as a positive 3y squared dy over dx. Now, all my dy over dx terms are on the left. I could factor that dy over dx out. So I'm going to use a little bit of algebra here. When I factor that out, the terms that are left are negative 4 minus 4y cubed plus 3y squared, and that equals 3x squared. So if my directions are to find dy over dx, to get dy over dx on this side alone, all I have to do is divide by everything that doesn't have a dy over dx. So dy over dx equals 3x squared over all of this mess. So negative 4 minus 4y cubed plus 3y squared. We have successfully taken the derivative or found dy over dx using implicit differentiation, getting the dy dx alone. So this is dy over dx, or the derivative with respect to x, the derivative of y with respect to x. An application of this is sometimes they will give you an ordered pair and ask you for the slope of the tangent line, and they'll have to give you an x and a y. Well, if they don't give you both, they would give you one or the other, and you'd have to find x or y, whichever one they didn't give you. And then you could plug those ordered pairs in to find the slope. In this equation, the directions are the same. Find dy over dx, or find the derivative of y with respect to x. This time I'm going to use a shortcut with my dy over dx. Instead of including that every single time, I'm going to do a y prime every time I take the derivative of a y term. And then at the end, I'm going to replace that y prime with dy over dx. I just think it saves some time not having to write dy over dx every single time you take the derivative of a y. So looking at this one, notice we've got two x squared terms. It is okay to go ahead and add the like terms before you take the derivative. It's not going to change the value of anything. So that would be 3x squared minus 4y cubed minus y squared equals 2x. And then if we take the derivative implicitly, that would be a 6x. We don't need the y prime because that's an x term, not a y term. For this one, that would be minus 12 y squared. We took the derivative of y, so I'm going to include a y prime. Minus 2y, that's the derivative of a y, so I include a y prime. And that equals 2, because that's the derivative of 2x. And that is an x term, so we do not need a y prime. Then I'm going to get the y prime terms together, and anything that does not have a y prime to the other side. So that would be a 2 minus 6x on the right-hand side. I'm going to distribute out my y prime. Then to isolate the y prime, I'm going to divide by everything that does not have a y prime. So I've got 2 minus 6x divided by negative 12y squared minus 2y. Then at that point, I'm going to replace my y prime. Since my directions said find dy over dx, I'm going to replace the y prime with dy over dx, just so that my notations in my problem match what the directions asked me to do. All right, and the next one, this one's a little more difficult because if you notice here, it does include the product rule. So we're going to have to use the product rule when we do this one. So basically, we're going to do the same thing. We're going to take the derivative normally. Anywhere we take the derivative of y, we have to take or put a y prime in there. So if you look at this, in this term, that would be the product rule. So there, the first term is a negative x. The second term is a y. So if I take the product rule and do that, take the derivative of the first thing would be a negative 1 times the original second would be a y. Now in that term, we took the derivative of x, not y. So we do not need a y prime yet. For the second term, in the product rule, we do a plus the original first part, which would be a minus x, times the derivative of the second part. Well, the derivative of y is y prime. So if that's plus a negative, this would be a minus. In this term, that would be a minus 10y. That is the derivative of a y, so we need a y prime. plus 7, the derivative of that is 0. That equals 0 because the derivative of 16 is 0. A common mistake that I see my students make here a lot is they forget that the derivatives of the constant terms are 0, and they keep the 7 and the 16, end up with a 9, and that messes the whole thing up. So be careful when you take the derivative. Don't forget the derivative of a constant is still 0, even though this is a little bit more complicated. And then everything that has a y prime, I'm going to leave on the left. Anything that doesn't have a y prime, I'm going to move to the right. So that means the y ends up being on the right-hand side. I'm going to distribute out the y prime. And then I'm going to divide by everything that is not y prime. So I've got a y over negative x minus 10y. And the y prime is here, which is the same thing as dy over dx. I just changed my notation to match what the directions ask me to do. With this, if you wanted to express that as negative y over x plus 10y, that's fine. It doesn't matter. And then there are a lot of applications we can do with this later. We can find the equation of tangent lines with this still. The related rate problems, as I said before. When you do related rate problems, a lot of times you not only have to find the differentiation implicitly with the y, but also with the x or any other variables that you have. Anything in the problem that is changing, has a rate of change, we're going to use that y prime or x prime, whatever it is, to solve the problem.